Hello, and welcome back to day 2 of Approximation Week. Today I want to talk to you about splines, spline approximation, control points, interpolation, as well as computer graphics. Splines are one of the main ways that we use polynomials to approximate curves and other things. And what distinguishes them from what we just did with polynomial interpolation is that they are piecewise defined polynomials. What we do is we take a time interval, we chop it up into finite segments by using what are called knots, and within each 2 knots, we have a well-defined polynomial. But at each place where we have a knot, it's possible that we're going to have discontinuities, and we swap from one polynomial to another one. If you have followed my numerical analysis class last semester, then you saw us implicitly use splines. When we did numerical integration, we split up a region from A to B into a collection of equally spaced intervals. And within each one of those intervals, we used either a linear interpolation or a quadratic interpolation, and then we integrated those interpolating polynomials in order to give us things like Simpson's rule and the trapezoid rule and other things like that that allowed us to accurately estimate the integral of a continuous function, or 3 times differentiable function, all depending. But today I'd like to take that discussion a lot further. I'd like to discuss how splines are used in computer graphics and approximation theory. So back in the 80s and 90s when I was growing up, my dad was a huge tech nerd. We had computers, we had gigantic printers, we had a ISDN line, and you have no idea what that means, and that's okay. Maybe it's just aging me. But a lot of really cool things were happening at the time. Back in the late 90s, you had movies like Toy Story come out, and there was a television series, ReBoot, that all used computer graphics. And even further back, you have things back in the 1980s where you could buy these VHS tapes that had showcases of computer graphics. They were absolutely fantastical at the time, but when you go back and you look at them, they're a little cringy today. So after hunting around on YouTube, I ran into this old archived documentary by Pacific Arts. And inside of there, they had all sorts of examples of cutting-edge computer graphics from different studios in the 1980s. Some of this stuff, it looks so basic, it just looks comical to people in today's eyes, where basically sometimes you have spinning cubes or maybe just some water flowing. But really, each of them were very difficult things to design and put together, and we benefit from all of the advances that they made back then. Things like ray tracing or fluid flows and things like that were done on the computer now is just typically integrated into things like 3ds Max and Maya and even Blender, which is free to download right now. One interview that they did with a group called Able Image Research really stood out, where the company was tasked with making a commercial that had never really been done before. The actual construction was really fascinating. They go through and you can see pictures of these really old computers, giant CRT monitors, big dials that they have to play with in order to make things work. They have tape drives, and they're designing a 3D model of this robot that's supposed to be animated, have arms, legs, finger joints, all these things, and they had to put it together without any of our modern tools, where in an afternoon you could probably make exactly the same model if you had the right skill set. These people had to take a physical model that they made out of foam, cut it into slices, and then trace out each one of those slices and scan it with a little handheld scanner to get it into a computer. And then when you look at them playing around with the dials and zooming in and zooming out and rotating, you can see that the way that the information is stored inside the computer is as a whole collection of curves that just sort of spin around and define an entire level. So the robot itself ends up being defined in terms of slices, and each slice was defined by a curve. There's a lot of ways to represent a continuous curve, but the most likely way that they were representing it would have been using splines. Splines are piecewise polynomials, so they're very easy for a computer to evaluate. With a spline curve, you only really need to define a finite number of points, and then using those finite number of points, the computer will try to interpolate or come up with some sort of fit within a convex hull of these what are called control points or interpolation points that will match them exactly. So it's really fascinating seeing all this being used.
Even in the year 3000, the question will be, what's a blood? We see the brilliance of food in cans.
Even today, we see big 3D companies using splines and coming up with new routines to integrate splines into their workflow. For instance, Fusion 360 released an entire article that goes over how they are changing from using interpolating splines to control points, because control points are a little bit more intuitive as far as the shape you get at the end, where Fusion 360 is used to make 3D CAD models for engineers and scientists. So now what I'm going to do is I'm going to go take you through some of the basic theory about splines and spline theory. We'll talk about the de Boer algorithm using control points and to define a spline curve. And I'm also going to talk to you about interpolating splines, where we'll need to have a Gram matrix made from our splines that will invert to match exact points. Now, the things I'm going to have to define here are going to be things like B-splines and spline space. But before we do that, I kind of want to get a little bit more comfortable. So why don't we go back over to my office and we'll start talking over there. Well, that took all day. Since I recorded that last segment, I've been more or less just coding up the B-splines code from scratch. You truly don't understand a problem until you actually go and code it up and confront all the little difficulties that can come up, that can come into play as you're implementing it. So the setting here is that we have something like a curve in 3 space, and we would like to be able to represent it with splines. It wouldn't be a perfect representation, we're aiming for an approximation. We could use things like polynomial interpolation or kernel functions or other things like this, but splines work really well in this situation, and there's a lot of algorithms that we can try to employ in order to make this as good as we can. So a spline is a piecewise defined polynomial, and we need to pick the segments of our interval, say 0 to 1, that we've parameterized the curve over, and we need to segment it so that we can define the regions where it is going to be a polynomial and where it switches to a different polynomial. Once you've fixed these knots, which are the points where you swap from one to the other, you've defined a sort of spline space. It's a vector space of all splines with those particular knots. And what we would like to do is we would like to take a particular spline out of that space and use it to represent our curve. Now, one other feature about spline space is we're going to fix a maximum degree to the polynomial. Each segment will only have a cubic or a quadratic polynomial on the inside, or even linear, and we'll use that for doing all of our approximations. So we need to pick a basis. And one basis is called the B-spline basis. It was shown to be a basis by Curry and Schoenberg back in the 1950s or something like that. I might be really off on that one. But the B-spline basis is an excellent basis to use, and in this lecture we'll actually use it in 2 different ways. We're going to use what are called control points, which are sort of suggestions of where a curve should go, and we'll also use interpolation, where we say that a curve has to go through particular points. Both of these have their advantages, where the control points doesn't take the points too seriously, so if you have a lot of noise in your system, you don't always want to trust the actual samples you got too much, you just want to know that they're kind of in the ballpark of where you want to be, whereas interpolation might overemphasize noise. But at the same time, with the interpolation scheme, we have some really nice convergence results. So if you know that you have fairly decent and clean data, you can make guarantees of how close you're going to be based on the knots you chose and the order of the polynomial. I'm trying to make it not completely obvious how tired I am right now, but I don't think I'm really winning on this count. So this B-spline basis is actually pretty neat. You essentially define characteristic functions or indicator functions for when you're over different segments between 2 knots. And right now I'm sticking to what are called simple knots, so I'm leaving out multiplicity of knots, which does add a whole other dimension to spline approximation. And so if you take any pair of 2 adjacent knots, in between there is an interval. The order 0 B-spline is simply the indicator function for that interval itself. So it's going to be 0 outside of there and 1 inside the interval. And then you use this in order to construct higher order B-splines. So you'll take your constant B-splines and you'll use a sort of combination of them in order to make the order 1 B-splines. In particular, what you do is you take the jth order 0 B-spline and the j plus first order 0 B-spline, and then you multiply them by 2 linear functions. And by using these linear functions, you're essentially just going to be making a little hat function that just interpolates the 1 knot at 0, next knot at 1, and the next knot at 0. And one thing that's particularly important to note is that when you move from the 0 B-spline, each of these splines has a support of only 1 of those knot intervals, but then the order 1 splines has 2. And then if you want to make an order 2 spline, you're going to do the same sort of thing, but then recursively you end up recruiting another interval for your support in your second order B-spline. This means several things. One, that means our splines are getting wider, and the area of influence is also getting wider. But if we're sticking with the same knot set, that means that if we go from order 0 spline to an order 1 spline, we lose 1 spline. And then we go to order 2 spline, we lose another spline. So if you're working with a data set, you need to make sure that you have enough knots in order to maintain the sort of flexibility or the dimensionality that you want out of your splines to match up with your data after you've done the augmentation to making them from order 0, order 1, order 2, order 3, etc. And so there's a general recursion, and it more or less follows exactly the order 0 to order 1 splines. And essentially, you take a look at your previous order splines, and you take the jth one, and then you take the j plus first one, and you multiply each of those by a particular linear function. And once you do that, you make your next order spline. And that's it. It's a super simple algorithm. It's just a little bit of bookkeeping and make sure that you're using the indices right, and it can be a bit of a headache, but it's not too bad at the end of the day. B-splines have a lot of nice properties. For one, all of our B-splines end up being positive functions. And they also satisfy what is called a partition of unity. So within a certain region, after you've taken away the leading knot intervals and you trim off the trailing M knot intervals, if you sum all your B-splines together, you're gonna have a flat 1 for every T. And that's because they partition the number 1 among all the splines. And it also comes up when you take a look at, say, Bernstein polynomials. They also have the same feature. And so this really helps their ability to do approximations, especially when you're talking about things like control points. Now, the control point method basically takes a collection of vectors that all correspond to points on your curve, and it slaps them one at a time on each of the B-splines. If you take a look at your B-splines, they all basically achieve a highest point and then decay to 0, and then eventually are 0 for all of their T. And so what happens is if you hit that with a vector, say dj, and apply it to the B-spline j of order k, then when that spline is at 1, all the other splines cannot be at 1 because we have a partition of unity, which means that that vector itself will be the result of the overall approximation. And then as time marches forward, that vector is going to be de-emphasized and a new vector is going to be emphasized on the next spline. And then that one is de-emphasized and the next one gets emphasized. And this is the sort of the control point method. The B-splines aren't always going to be 1. They might be like 0.7 or something like that. But each one will sort of take a dominance in a certain region. And this is how the control point method works. And more than that, if you're okay with this sort of control point approach to the problem, it doesn't give you a perfect interpolation of all the points that you sampled, but what it does do is it gives you a really fast algorithm. The control point algorithm is really just a big O of n, or for any particular t, you just have to read out the vectors from the curve that you want to approximate, and then hit them against some B-splines rather directly. You don't have to do any matrix inversion or anything like that, and you win. And that is your approximation. Now, interpolation, on the other hand, goes back to what we were doing last time, where we made a van der Waals matrix to find interpolating polynomials. Although in this case, we're not going to be hit with Runge's phenomenon in the same way that we were before. And a big reason for that is because these are piecewise defined polynomials, which means that an earlier point is not going to have as much influence on the decision that we do later. So for interpolating polynomials, any new point that we added is going to affect the chain all the way down. And that still happens to an extent, but it's a lot less now because we swap which polynomial we were talking about over each interval. So the algorithm is more or less the same as a van der Waals one. You basically have a whole bunch of coefficients that you hit against your B-splines, and then for each particular ti, you want to make sure you match up with, say, some yi. We'll think of this in terms of being just one-dimensional, but if you want to make this higher dimensional, we can just stack these on top of each other and just do the inversion over and over again. So what you do is, for any particular ti, you evaluate each of your B-splines at ti, and you know that if we take a linear combination of these according to some vector, say w1 through wn, we can basically do that whole row times column thing. That should give us yi. And so then you do this for t1 and t2 and t3 all the way up to tn, and there you go. That is your inversion. I'm going to choose all these t's to correspond to my knot points. And when you do that, you have certain guarantees as far as convergence rates. in this book that I generally refer to, it's a fairly simple book to get to, and they get to the results fairly quickly. And so on page 88 in here, they actually give a nice convergence result for spline interpolation, where basically you have the difference between the function that you're trying to interpolate and the spline interpolation, and so you're looking at this in terms of the soup norm. And it turns out that this is big O of a norm that involves your knot points times the Sobolev norm of your function in your space. Now, the interpolating polynomial is a little bit more complicated than what we're talking about here, and this comes from adding multiplicity to the knots at either point of your interval. Basically, we want to have our spline to not only have piecewise defined polynomials, but at either endpoint of, say, A or B or 0 or 1, however you want to look at it, for each of them, we basically want all derivatives of order k up to 2k to be flat 0. And then once you satisfy those conditions, then ta-da! You have what are called natural splines, and these natural splines give you this approximation guarantee. Okay, so that's the control point method and spline interpolation, but why don't we go ahead and see that in action? I was looking for a nice example to do in this class, and I realized I can make a curve really quickly just by doodling on my tablet. And so I'm going to show you how you can actually turn that into a whole bunch of, how you can turn a video of you writing into a whole bunch of control points that you can later use for doing some approximation with splines. So why don't we go ahead and take a look at MATLAB and we'll jump into it. Okay, so since I recorded that last segment, it turns out that I lost all the footage from the MATLAB portion. So I'm just gonna have to do all this again, and maybe I'll do it better this time. So what we're gonna do is we're gonna do two things. We're going to first write up some B-spline code, or at least I'll show you the B-spline code that I have done. Now what I'm gonna be doing is I'm gonna be throwing this into what's called an anonymous function inside of MATLAB. That's basically where you define a function in terms of an @ symbol. These aren't the fastest things in MATLAB, but they do the job, and they allow me to quickly package a recursion. So with this recursion, basically what I'm going to be doing is I'm going to have a whole column of my B-splines, and so it's going to be each one of the B-splines I have is going to be, think there is one column and it's going to be several rows. Each row is going to correspond to a different one of these B-splines. So I can basically take this vector that I get of my B-splines, and I can multiply that by my control points, and then that's the control point method, so it's really simple. Now, to make the first one, what I'm going to do is I'm going to basically use two logicals. Remember, the order 0 B-splines are basically indicator functions for the intervals between two different knots. So what I'm going to do is I'm going to basically use a logical that asks, is x bigger than this knot? Is it less than this knot? And then I make a whole vector out of those. All I really need to do is make a vector out of my knots and ask, is this real number bigger than the vector of knots? And MATLAB will actually turn that into a vector of logicals, and so that's easy enough. I turn that into a double so I can multiply using it, and then I do the same thing to figure out if it's greater than and if it's less than, and I multiply those two. Then that gives me my characteristic functions. And using that, I build up my order 1 B-splines. And to do that, I need to have a special function that will select individual members of my of an anonymous function. Anonymous functions, you can't just use the typical MATLAB vector tricks, so you need to actually throw that into another function that extracts those vector components. Then I can construct my order 1 splines by taking a look at the first spline I made that was order 0 and compare it to the second spline that was order 0, and then multiply it by a particular linear function. And then I take a look at the second one, and then I compare it to the third one, and I multiply it by another linear function, and etc. So for the first chunk in my recursion, I'm selecting from 1 up to, say, the next to last B-spline. And for the other one, I'm going from the second to the last B-spline, and then I'm multiplying these by particular linear functions that correspond to my knots. And you'll see what those look like in here. And then once you do that, you just keep running a loop, and then you can get higher and higher order B-splines, and yeah, that's the whole algorithm. So then after that, I'm just gonna run some plots, show you what those look like, and then we'll go ahead and do the writing example that I was talking about. And that takes a little bit of pre-processing. It starts with a movie file I captured from my tablet, and then I upload it to my computer. And after that, We do some pre-processing, we use some logicals to make things black and white, average other things to make them grays, and then zero those out, and then I extract control points from them. So let's go ahead and take a look, and I'll explain the things as I go. So here we go. This is the B-spline maker, the algorithm I made to make B-splines. And these are my knots. So I'm looking at the interval 0 to 1, and I'm choosing a knot at 1/10, 2/10, 3/10, 0, and 1. I want an order 3 spline polynomials, or order 3 splines. So I choose this m character to be 3, and this is an auxiliary function that, an auxiliary quantity that's nice to keep track of. Right, so this is where I'm going to evaluate for all my plots, and this is where I make the first B-splines. So these are order 0 B-splines, and these are just characteristic functions. So these are the logicals I was telling you about earlier. So then all I need to do is to plot this as I evaluate n at all of our evaluation points, and let's go ahead and see what we get out of this. So there you go, there are your characteristic functions, and so this one corresponds to the interval between 1/10 and 2/10, and this one between 5/10 and 6/10. I didn't plot all of them because it would just be a big mess, and so I just plotted these 4. But that's what we're working with. So then, this is an auxiliary function just to select particular entries in our vector of B-splines, and I run a loop to increase the order. So let's go ahead and see what that gives me. There you go. These are my order 3 B-splines. So you can see that where the other ones were just had a support of, say, 1/10 to 2/10, this blue guy has a support that goes from 0 all the way up to 4/10. So order 3 polynomial requires 4 of our knot intervals for its definition. But then after that, it's just going to be 0. And if we take a look at what happens when we add all these together, so the sum of all these plots, what do we get? Well, we get a flat 1 from, say, about 2/10 to about 8/10. And so this is the partition of unity interval that I was talking about before. So if you look at it, basically I am selecting my 1 to n plus m minus k entries for my B-splines. So this is my n is my last version of my B-spline, and I'm multiplying it by this linear function. Now this is actually a vector here, and this is a vector, and this is a vector, but in the way I multiplied all of them, it basically enacts all of the linear terms I need to multiply and makes them as just one vector that you then multiply entry-wise to your column of B-splines. And then I make the second term, but here I select from 2 to n plus m minus k plus 1. And that's it. That's the entire recursion. It took a little bit of fiddling in order to get all the coefficients and everything right, but it works out pretty well, and so I'm pretty happy with it. So now let's see how this whole control point thing works. So what I'm doing is I'm using the image processing toolbox, and it asks me to make 7 selections. Now it says 7 just because we have 7 B-splines, and that's the amount of flexibility we have in what we're working with. And so there we go. So this is the control point method. These are the control points I defined by clicking around, and you'll notice that it doesn't actually match any of them perfectly, but every single time point ends up being a convex combination of these 7, where that convex combination leans more towards this guy at the first instant, and this guy at this time point, and this guy at this time point, but it never actually matches any of them exactly. And that's because none of our B-splines actually reach an absolute value of 1, but what we do get is that we know that the sum of them gives us unity, and that's where the convex combination comes in. Okay, so those are B-splines. Now let's take a look and see what happens with this whole spline writing thing. So I have a video I recorded, and this is it. Just me writing an @ symbol on my tablet. And you notice it's a little wobbly in a few places. I mean, it's handwriting, and if you've seen me write on my tablet, you know I don't have the greatest handwriting. But in here, we're going to use splines to clean it up a little bit. So let me go ahead and run this code, and you'll see the result of all the pre-processing I talked about. So what we're going to get is a black and white image, and we're going to see a little leading edge that we're going to be tracing out. And should start up any second. There we go. So this is me writing, and I'm deleting out everything we've already seen and only adding the new entries as we go. And give it a second, and last loop, come on, and done. Okay, so these are control points that extracted, and this is what we're going to use in order to make our spline approximation. So if you look at the code itself, so this is where I load in the video. I'm going to comment that out in case we want to bring it in again. I saved the frames to a backup space in case I want to do some edits. And then I did this chop here. This is a little bit of pre-processing. For some reason, MATLAB read a whole lot of black lines in the top, and I just need to chop them off. And so this ends up effectively being a cropping. And then after this, I ask if a particular pixel, and this compares all the pixels all at once, are they less than 100? And this is because I'm saying 100 because I selected out of just one color channel here. Now, colors usually run from 0 to 255, and so basically I'm saying, is this, you know, less than a gray? Is this bigger than, or is this bigger than a gray? You know, 100 is about a dark gray. And so if it is, then it ends up making it black, and if it isn't, then it makes it white. So essentially all my white pixels are going to be sent to black, and all the black ones are going to be sent to white, more or less. So then I subtract 2 adjacent frames, and that gives me that leading edge thing that I was talking about before. And then I zero those out. So I ask, so we're going to end up having some negatives come out of here and some positives. So I ask, is my pixel negative? It shouldn't be. And if it is, make it say 1. And if it isn't, then make it 0. Then I end up getting a whole lot of little pixels out of it. So if I end up, I don't want to run it actually, so I got rid of these little extra pixels just by averaging top and bottom, left and right, and so then those become gray, and then I zero those out again. Then then this just runs through and goes through all my frames, and eventually I want to show them to you, and then I take the averages of the biggest white, the largest position of a white pixel that we've seen and the smallest position of a white pixel we've seen, average those together, and it gives us the pixel that we want. And so then what am I going to do? So that is what we want to write, and then for the spline writing itself, let's go ahead and push play. So this is going to use those control points, and it's only going to use 1/5 of them. That was a lot of control points that we saw before, and so I only want to use a handful of them because I don't want it to get too jittery. So I'm going to go ahead and push play, and there we go. This is the control point method, and it does it really smoothly. So we saw a little bit of wiggle in some of my spots in my actual writing, but those are gone here. We did lose this nice little cusp that we'd usually see when you're writing an @ symbol, when we make a turnaround on a piece of paper. You can recover that by adding an extra knot in this particular position here, and that will add a sort of measure of discontinuity and allows you to have cusps and other things like that in your spline curves. Okay, so now let's go and do a comparison and see what happens when you use interpolation. Now, interpolation, we're going to end up seeing something that's a little bit more jittery than what we were looking at before. And in order to do the interpolation itself, most of the code is the same as before for making the splines and the control points. But what changes is that we also have to make something which is a gram matrix. And so I basically evaluate each one of these splines at the place I want to actually interpolate, and then I make a matrix out of that. Then I have to invert it, and then I reassemble everything using those new weights. So, go ahead and push and play. There we go. And so you see the difference between the control point method and the interpolation method is that the interpolation method really trusts the points that we selected very strongly. And so you see a little wiggle here, a little wiggle here, and a little wiggle here. And yeah, in truth, that might actually be closer to what I wrote for the computer, but yeah, I mean, but it doesn't look as pretty and as clean as this guy. So it's up to you how you want to do it, but this is, this gives you two different credible methods of using splines. So now if we look at the code we have here for the interpolation, basically we got some weights that we inverted the gram matrix for on these control points, which end up becoming interpolation sites here. And then we use those weights and we multiplied times our splines. And that's what gave us the ultimate figure that you saw there. The difference with what happens with the control points is that we just take the control points and we multiply them directly by the plot. So there was an extra little matrix that comes into play here where we invert by the gram matrix, and then we use those weights that we got. So we have control points, we hit it with the inverse matrix, and then we multiply it by those weights that we get here. In this version, we actually just multiply by the control points. And so that is an algorithmic difference between the two. And this one ends up being a big O of n sort of problem, whereas the interpolating one ends up being more than a big O of n squared, because matrix inversion is slightly more than big O of n squared. So anyway, so yeah, that's the idea. And so yeah, so we end up getting both of these two figures, and that shows you how splines work. Okay, I think I'm tired of recording this. This is the third time I've recorded this, so I think I'm done. And yeah, thank you for watching, and I'll see you next time. And if you want... No, I'm just gonna stop there. Alright, cheers.